Hello, my name is John McLean. I'm an architect at AOL, and I'm also the lead developer of the cyclops-react project. So the goal of the cyclops-react project is really to integrate or unify a lot of these cool libraries that have emerged for Java 8 over the last 2 years. So we're talking about libraries such as glambda, functional Java, streamx, Javaslang, Reactor, RxJava, Drive4j, and others. The inspiration for it came from a tweet from Louis Ortola. We used to have a library called Simple React, and he suggested that we merge that with glambda and Javaslang, and it would be great that if we merged them. I think for a variety of reasons, it wasn't likely to be possible that we could do that. But I think the idea of maximizing the interoperability between these libraries and the broader ecosystem is one that's very valuable, and it's something that we spent a considerable point of time working on since. So one of the first challenges, if you want to unify this functional style ecosystem that's emerged in Java, is to actually unify the JDK itself. From a distance, maybe it appears that it's a coherent and consistent unified API, but in reality it's not. We have a lot of the same operators on types such as optional, stream, and completable future, but there's no common interface to them. And in fact, the naming across types is often completely different as well. So our starting point really is to figure out a way of how to unify the JDK and then move outwards from that, incorporating all of these really cool libraries that are out there too. So here we have an example of a Java 8 stream. We have a stream with a single value 1, and we're defining a transformation operation via the map operator. We're passing in a lambda expression here. This lambda expression is Java 8. If you're not familiar with the syntax, what's happening here is it represents a function with a single input parameter. The type is inferred, and it will be the same type as the stream, which is an integer. And then we're multiplying that integer by 2. So our stream of 1 will become a stream of 2, at least notionally, because stream is lazy, so map will be applied lazily, and nothing will actually happen until a terminal operation is called. But notionally, we're converting a stream with a single value 1 into a stream of a single value 2. We can do something very similar with optional. We can create an optional with a single value 1. We can define a map operator that accepts pretty much the same lambda expression that will multiply by 2. Optional is eager, so when this code is executed, we'll go from an optional of 1 to an optional of 2. And again, we can do something pretty similar with completable future. The one thing to note here is that the method names are different. Map has become then applied, but we're essentially doing the same thing. We're creating a completable future with a single value 1, and we're multiplying it by 2. And so on for collection types. We can also map or transform those. The only difference is we have to convert them to streams first and then collect them back into collection types. Conceptually, we're doing the same thing, it's just the code is a lot more verbose. So we have an array list with one value in it, 1, we stream it, we multiply it by 2, we convert it back into an array list, and we're left with an array list of a single value of 2, as per stream and optional completable feature as we've seen so far. So within the library cyclops-react, we're trying to provide a standard view across all of these types within the JDK and in external libraries. So the first challenge really was to provide a consistent API into dealing with futures. So the way we did this was create a future W or a future wrapper type that wraps completable future, and instead of calling the methods in the API things like then apply and then consume, we use the standard terms such as map and flat map. So in this example, we're creating a future W with a single value 1, and we're multiplying it by 2, and we have a future W2. But the code itself is consistent with the way that it's done in optional and in stream. But we can go further than this. We can define an interface that represents things that can be mapped over with a map operator within it. Standard name and functional programming for this is a functor, but I guess that isn't particularly important. What is important is that future W itself will implement functor, and as a result, we can assign future W2 a functor, and we can accept functors in as method parameters and return types and so on. So we have a way now to abstract over things that can be transformed. Just having a single type that can be transformed in itself isn't much use to us. We really need everything that can be transformed to implement this interface, or as many of those things as possible to get the maximum value from it. So what we've done in cyclops-react is we've created extension types for appropriate types within the JDK. So for example, we have list_x, which is an extended list, and set_x, pstack_x, and so on. And I'll come to what those are in a wee bit more detail in a subsequent slide. So in this example, we're creating a list_x with 2 values, or an extended list with 2 values, 1 and 2, and we're able to call map directly on that and multiply those by 2. List, in contrast to stream, which is lazy, is eager, so as soon as you call map, this operation will be executed and the transform will occur. Big benefit you're getting over the traditional way to do it with arrays as list, stream, map, and then followed by collect is that your code is much less verbose, and indeed we have a way to abstract over the transformation operation. So within cyclops-react, we've created these extended types for as many as possible of the various JDK types. So for stream, we've created reactive seek, which is an extended stream. Now, reactive seek itself not only extends JDK stream, it extends dulambda's seek type. So within the dulambda library, what they've done is create this really powerful sequential stream type called seek. The reason why they created this was that they realized stream within the JDK has quite limited functionality, and the reason why it's limited is that it has to accommodate both parallel processing and sequential processing. And the insight that they had was that by creating a sequential only stream, they could add a lot more powerful operators to it. And what we've done in Cyclops-react is extend their sequential stream type seek with our type reactive seek, which adds in elements from reactive programming, things like dealing with asynchronous operations, error handling, and that type of thing within the stream. Within Cyclops-react, we go one step further again with our lazy future stream type, which in turn extends reactive seek, which extends dulambda seek, and in turn stream. It layers back in parallel execution. It takes a different approach to the approach used in the JDK, which is why we're able to offer a lot more operators with parallel execution. Under the hood, we're using futures to distribute tasks across the cores. It's particularly efficient for handling I/O operations versus CPU-bound or heavy computational operations. So optional is a final class, so our approach here was just to create a new type. I think we've added some value by doing something different. Maybe is our optional type. It implements all of the new interfaces for abstracting across things like transformation operations and others, as you might expect. It differs from optional within the JDK primarily in that it is lazy, so its operation is much more like a stream maybe of a single value that can represent something that can be either present or not. With completable future, we've created this future W delegating wrapper class over a future, and for the various collection types, we've created extended interfaces such as list_x, pstack_x, pvector_x, set_x, and so on. The types that have P in front of them, P stands for persistent here, and the JDK types are by their nature mutable, but you can make them immutable. The challenge though, if you want to change a value or a single value within a JDK collection that's been made immutable, is that you have to copy the entire data structure just to change that single value. With persistent data structures, you can evolve them much more efficiently. So what we've done is we've created a set of interfaces that represent extended persistent data structures. And then finally, there is this super powerful extended type that we've called NEM that can extend and wrap any type that implements map and a number of other operators from right across the ecosystem, and we'll touch on that briefly later within this screencast. Okay, so why does this matter? Why is it important to create these abstractions over operators that are there in the JDK and across other libraries? Well, the reason we believe it's important to have this is that as you get into using things like streams and optional, and you may have come across this in your code already, is that you can wind up, for example, with complexity emerging. For example, deeply nested map and flat map operators and so on. There's a lot of different things that you might try to do that wind up being very complicated to do with the APIs that are provided to you. But you can go out and you can solve that problem. So for example, in this example, we have a a reactive seek or stream type, a reactive sequence with 3 values, and then we're creating a range of values inside the flat map operator, and we're creating then a tuple from that and pairing off each of the values from the 2 streams. So we're getting all the combinations of values from the 2 streams. And you can imagine that if we were to try to do a flat map again and have another nested layer beneath this would get very, very gnarly. A standard way of simplifying this type of operation in other languages such as Scala or Haskell is to use for comprehensions. Java doesn't have these natively, and it's quite gnarly to implement them because, as you can see here in our second reactive seek, in the range operator, we're referencing the current value from the previous one, and implementing this in Java is not trivial. Do we really want to go through the process of solving these non-trivial problems for every single library over and over again? Or is it better that we have a way to abstract over these concepts and then solve them once in one place and then reuse it? We're of the opinion it's better solve the problem once, reuse it, and move on to something new. So just to show you, this is an example of a for comprehension. This is doing exactly the same thing as the previous code, except for there's no nesting of operators and so on. It's a little bit cleaner. And this is a for comprehension for a reactive seek that accepts a reactive seek. We can also, once we have this way of abstracting over map and flat map, define the code that implements a for comprehension once, and then we can simply reuse it across libraries. So in this example, we are reusing that code that we've written once to implement for comprehensions for pivotal reactors flux type. It's doing exactly the same thing as the previous examples. Okay, so we've touched on our approach to unifying APIs across the JDK and why we think going out there into the world and unifying the libraries themselves is important. So it might be worth discussing how we can, as a community, unify our libraries so as to get the maximum benefit for all this innovative work that's happening in the Java 8 ecosystem. So the Reactive Streams API that's out there, that's going to be essentially incorporated in Java 9 as the Flow API, is something that we feel really passionately about, that is very valuable in maximizing interoperability between libraries. So the Reactive Streams API really defines a way of publishers or producers of data interoperating with consumers of data. And let's see how that works. So this is an example. It's purely from Pivotal's Reactor project. We're creating a flux, which is their version of a stream. It has 2 values, 1 and 2, and we're performing a flat map operation in this. This is pretty similar to the previous example where we're creating a nested stream within a stream. The flattening map operation will result though in a single stream of integers as a result, and we'll print those out to the console. So far so good. This is just Pivotal Reactor on its own. But Pivotal Reactor implements the Reactive Stream spec. All of its types, where appropriate, are Reactive Streams publishers, and they also accept Reactive Streams publishers as well, where appropriate too, within their APIs. So within cyclops-react, we take the same approach. We implement Reactive Stream Publisher where appropriate and accept it within our APIs. And if you're out there creating a Java 8 library, we would recommend that you do the same thing too, because you get this nice interoperability for free. Essentially, the code hasn't changed much except for we've changed the type that we're dropping in here. But as you can imagine, if developers out there, there's a lot of different libraries they can potentially use. Maximizing the interoperability between them is valuable then for the consumers of those libraries, because you may not be able to just limit yourself to libraries that are built using Pivotal's Reactor. You may also want to use libraries that are built using Javaslang or cyclops-react or functional Java and so on. So because we implement publisher within Reactive Seek, we can just drop it into the Pivotal Reactor flux type. And vice versa, we can drop Pivotal Reactor types into Cyclops-react types because we accept Reactive Streams publishers within our types. And there are other benefits as well. I mean, Pivotal Reactor is obviously very, very focused on the Reactive Streams world, and they've created a ton of functionality and very useful, helpful methods for dealing with publishers. Typical operators from reactive extensions such as A and B are ambiguous, which accepts the fastest or returns the fastest data source out of a number of publishers passed into it. So in this example, we are passing in two reactive stream publishers to the A and B operator. One is a reactive sequence of 1, 2, 3, and the other is a flux of 10, 20, 30. Now these values are all present immediately. They're canned values. So source 1, when demand is signaled on it, is going to return immediately, and that is ultimately going to be the result. But you can imagine a world in which our publishers have data that arrives asynchronously, and in that case it could be source 1 or source 2 that gets returned. But the nice thing is that because cyclops-react types implement publisher, they just fit right into the Pivot Reactor helper methods for dealing with reactive extensions. And we'll show how cyclops-react can help you drop in types from Javaslang and functional Java and other libraries in a moment. And this works both ways. When you get your result back from the A and B operator, if you want to convert that into an extended collection or any other type in cyclops-react, you can do that directly because cyclops-react types accept reactive streams publishers. And you can do this then as a one-liner, and you'll notice that the interoperability is quite clean and direct between the two libraries because of this nice third-party API or standard that defines how data publishers and data consumers should interact. So Javaslang and functional Java don't implement the reactive streams spec directly, but we'll show you a couple of techniques that can help out here. So the Cyclops Javaslang project provides a mechanism whereby you can coerce any Javaslang type to a reactive stream publisher, and Cyclops functional Java does exactly the same thing for functional Java. You can take a functional Java stream and convert it into a reactive stream publisher. Once you have this, now you can drop them into the nice helper reactive extension methods in Pivot Reactor and convert to any other type, such as setx in cyclops-react that accepts a publisher. So we're getting this nice interoperability across 4 libraries by virtue of the reactive streams interoperability. So while Javaslang doesn't implement reactive streams API, it does make very good use of the iterable interface. It's a core part of the JDK. There's a certain overlap between iterable conceptually and reactive streams publishers. In fact, you can implement a reactive stream publisher in a pretty straightforward manner using the JDK's iterable interface. So just like in Pivot Reactor, where the flat map operator can accept as a return value to the function provided any type that implements reactive stream publisher, within Javaslang, flat map will accept as a return type anything that implements iterable. In your library, if you have your types implement iterable where appropriate, they can just plug right into Javaslang. So here we have a cyclops-react lazy future stream being returned as part of a flat map operation on a Javaslang array. And again, we would encourage you to also consider accepting iterable where appropriate within your API. So here in cyclops-react, we accept iterable in our API where appropriate, and now you can just drop in Javaslang types directly in there where appropriate too. In functional Java, they have their types implement iterable, so you can drop them into flat map operations and so on within Javaslang and get this nice interoperability between Javaslang and functional Java and so on. But unfortunately, the reverse isn't true. Within functional Java, probably for reasons of strictness, they require that you return the actual functional Java type, typically from operators such as flat map. So that is us blocked, but is there anything we can do to help out here? So what we've done in cyclops-react to try and solve this problem is provide a wrapper class around any Java type that has a flat map and map method. So we can wrap a stream from functional Java just as well with this type as we can a stream from the JDK or from Javaslang, a Javaslang array just as well as we can a functional Java list, for example. And this wrapper class, which is called NEM, itself defines a flat map method. Once we have a functional Java stream wrapped inside a cyclops-react NEM, we can call the flat map method on that, and it can accept there is a mechanism for it to accept a Javaslang array or any other of these types out there across the whole Java ecosystem that implement flat map as well. So in the example code that we have here, we're basically assigning a functional Java stream to cyclops-react NEM by wrapping it into an NEM wrapper. And we're doing the same for the Javaslang array. Once the two types two instances in this case are wrapped in the NEM instance, we can then flat map between them. So in this case, the cyclops-react NEM is just simply acting as a glue code between functional Java and Javaslang. So for developers, what that means is that if within your project you've decided to use Javaslang, but it turns out that there's another team who have produced a set of libraries that you would find very useful, but they've written them in functional Java or in Cyclops-React or using JDK types, doesn't mean that you need to sacrifice interoperability. It's possible to get these libraries to interoperate very, very smoothly, even though the library authors may know nothing of each other or the existence of those libraries at all. So this has been a brief overview or introduction to Cyclops-React. It's roughly based on a presentation that we give at OSCON back in May, slightly cut down. There's more stuff in that presentation that we may produce another screencast for, but hopefully this has been an interesting introduction for the people that have stayed listening this far through it. If you have any questions, please feel free to reach out either via the GitHub site for Cyclops-React or on Twitter at Cyclops_AOL. Thank you.